All right, welcome everyone. This is Deep Learning Adventures, a fun and engaging meetup where we talk about deep learning and cool applications, including natural language processing. So this is our second adventure on NLP. Last week, David and Robert did an amazing job of covering sentiment analysis, tokenization, and some of the prerequisites, I would say, that are needed before we dive into sequence models, which we'll do today. So many thanks for that. If you weren't able to attend us last time, we have recordings on our website, on our bit.ly Deep Learning TF URL. You can always see all our recordings there. Cool. So today we're going to talk about sequence models, and as a motivation, if you remember from last time, we were considering, remove ourselves, the challenge of classifying movie reviews, and we were looking at the subword tokenization of IMDB. And basically the challenge there was that each word wasn't a token, but actually parts of a word were actually tokens. And we had about 8,000 such sub-tokens or subwords. And the challenge there was we couldn't really classify a movie review as positive or negative properly. We achieved about 50-something percent, 54% accuracy, and the main reason was that subword meanings don't really have a lot of meaning. We need to consider the order in which they appear so that we have a better result. So speaking of pointer, perfect. Speaking of sequence models, what is a sequence model and how does it compare to what we've seen so far? So this is an image that I pulled from an amazing blog from Andrei Karpathy many years ago, from 2015, I think, on how efficient and how effective are recurrent neural networks and what do they do internally. So here on the left, you see an image of, in red, it's the input layer or the input features. In green, it's the actual network that does all the processing, and in blue, it's the output layer. So far we've seen an input to our network and an output and all that. We can apply this multiple times. We can apply this on a large data set. We can apply this in mini batches. We can stack multiple such networks together. We can have multiple green such boxes that are related, that are stacked vertically, and that makes our deep network. What is different here is that we reuse the same network again and again. And not only that, but we also keep track of an internal state that is stored in such a network. And before we take a deeper dive, some higher level applications or some higher level visualizations that hopefully will help us get an idea of sequence models is, okay, so this one-to-one is one such architecture. What other architectures are there? Another one is you could feed some kind of feature or input, and you can generate multiple features or multiple outputs. And in this diagram here is, you could have, for example, an image captioning. So it could be a feature, for example, from a convolution neural network that we've seen in the past. It could be the very last or the second to last layer, which has those rich features at a very high level. From there, we can train a network to actually generate the actual caption, and that's something that RNNs and CNNs are used in combination. Another thing we can do is, what we're actually going to try today is actually look at reviews or look at text and actually just give only one output, and then output would be positive or negative. So that would be a many-to-one mapping or many-to-one architecture. Another one would be we receive a sequence as input. We do some kind of a processing and we output another sequence. An example of this would be maybe when you're doing translation from, let's say, English to Spanish or English to French. You have a sentence in one language, you do your processing, and you output a sequence in another language, possibly of different lengths. They don't have to match the same length. So that's called many-to-many. When the lengths have to match exactly, then that's a special case of this, of the previous architecture, where now the lengths actually match and that there's a meaning. Now, maybe they're time constraint, like in this example, Andre was talking about classifying each video frame. So maybe you want to classify if this is some kind of action frame or comedy frame or something else. That would be a many-to-many, where the input size also matches the output size. Cool. Any questions regarding this diagram? I thought it was very useful before we actually take a deeper dive on this sequence models. Okay. Then how do you actually make one of these modules work? You need two things. You need weights and biases, as you know. So we have weights and biases. Sorry, I'm meeting somebody else. We have weights and biases for the input. In this diagram, they're called WXH. X is the input notation, H is the hidden cell notation, and Y is the output. So the difference here is that each cell or each network here has an internal state, and that internal state is also used as an input in the next time step. So how do we do a forward pass in one of our, in a recurrent neural network? We take as input X. We have an internal state called H that is defined. We have our input X. We multiply them with separate matrices, WXH and WHH. We add them up. We pass them through a nonlinear function, tan H in this case. And that's our new and updated internal state. So our internal state, our next step internal state depends on the previous step internal state plus the current input. And then a modified version of that internal state, in this case by this matrix WHY, will be our output Y. So really the key is that there's some kind of recurrence here where the current hidden state depends on the previous hidden state and the current input. So yeah, so in this case, our input is a character, and edge character is here is looks like it's one hot embedded, where basically one character has a one in only one dimension or one location of the index, and zeros everywhere else. And our goal is to predict the next character. So if our network is trained properly, we would input H as our first input. Our network would have an internal state. We would output a softmax, or we would output a vector, and hopefully the highest index or the highest probability index would correspond to letter E. Then we input E. Hopefully it outputs L. We output L. Hopefully it outputs L. We output L again. Hopefully it outputs L. So that would be predicting the word hello. Cool. Let's take a slightly deeper dive into this architecture, and from the very basics, see how can we implement this at a high level. So these slides are from MIT's Introduction to Deep Learning, a very great job on explaining from scratch how a recurrent neural network works. So let's say somehow we've implemented that previous class that we saw before on updating our networks. We need two things. We need to initialize our hidden state. In this case, it's a 4-dimensional hidden state. We need an input. This would be our input X. And all we're doing, actually, we're running the same model here, RNN, which is using the same weights and the same biases again and again. We're using our current word as input. We're using our current hidden state, and we're producing an output and an updated hidden state. Then we go in this loop again. We use the updated hidden state and the new word, and we predict the next word. We use the current hidden state, the new word, we predict the next word, and so forth until we reach the end. And hopefully, after 4 words, we would have predicted hello recurrent neural networks.
Oh, okay.
Yeah, if you have any questions, yeah, feel free to unmute yourself and go ahead. So visually, the architecture is we have an input X, we have a cell which has an internal state HD, and it depends on the time t. That's why you see this lowercase t. And it outputs a prediction or an output yt that also depends on x and h. And that is used again and again as many times as we wish. If you really want to implement this from scratch in TensorFlow, you can do this. You can extend the layers class. You can initialize your 3 weight matrices. You need one for the input, one for the hidden state, and one for the output. You can initialize the hidden state to zeros, And really, you just need to define the forward pass where you multiply the hidden state with its corresponding weight matrix, multiply the input with its corresponding weight matrix. That produces your updated hidden state. And then a modified version of that hidden state is your output. And then you just return your output and your hidden state. This is if you want to implement it from scratch on your own. And TensorFlow has implemented this very network here under the class called simple RNN, where you just have to specify the dimensionality of this hidden state, which this is RNN units. Cool. A little more theory before we actually go to the practical applications of this. If you remember from the beginning, the way we train networks is we do a forward pass, we predict the value, we compare that value with the actual value or the labeled value, and we calculate a distance metric or a loss. That loss allows us to update our weights and biases going backward. So this same architecture here on the left, which is a recurrent visualization. On the right here, we have what is called the unrolled version of it, or basically if you wanted to look at this network at different time steps, it would look something like this. At the first time step, we'd have the same network, using as input the first input. And there are 3 weight matrices that we have to keep in mind. And it produces an output and a hidden layer. That hidden layer is actually used as input in the next time step with a new input, produces an output and a new updated hidden state. So we do this for many times. And what we do is we take all our predictions, y1 to yt hat, we add them up. That defines, we take the loss from all these predictions, we add all these losses up, then somehow we need to backpropagate all these losses and update all our weights and matrices, all our weight matrices, which is really 3, throughout our network. So this process is called backpropagation through time. And what it really does is basically keeps track of now our derivatives actually depend on the time step. So that's why it's called through time. Cool. Some issues and some challenges if you try to implement this, and especially if you implement this and if you run it multiple times. So,
George,
go ahead.
Could you go back to how does the individual time step losses and the grand loss, so if you average them or sum them or whatever, what gets fed back? Like for the last one, does L3 get fed back as the loss, or how does L relate to L3 or to any LT?
So L3 depends on YT, which depends on the input. There are 2 inputs actually, the input and the current hidden state.
Right.
The current hidden state though has information and dependencies on all previous inputs as well as all previous hidden states. So the chain rule here would be recursive, and this loss is actually a function of all the previous losses. So I don't think just taking the last one would be enough. I think you just take the summation of all these losses and you try to update the weight matrices in parallel. Or basically you'd have one giant loss, and this giant loss would depend on all the inputs as well as the current hidden state, but that current hidden state would depend again on the inputs as well as the initial hidden state. There's an initial hidden state here.
Okay.
Yeah, there are many of these courses, they actually go through the derivatives and the chain rules and all the mathematical notation of this. I didn't include it here for brevity of time.
George, so with the hidden states, they also have the previous inputs as well. Those hidden states also have the previous inputs as well?
Yeah, they depend on it, yes.
Okay.
Yeah, so if you see here, the hidden state depends on the previous timestamp hidden state as well as the current input, X. So when you calculate the derivative of this, you'll see that it depends also on the input.
Okay, thank you.
Yep. So one challenge that standard, this is called standard as compared to other ones that we'll see soon, have is that many of these gradients could be either too small or too large. So, so using the chain rule, basically we're going to have multiple factors multiplied together, and if many values in this long multiplication are more than one, we're going to have a problem called exploding gradients, where you multiply something that's greater than one, eventually it'll get out of control and you'll have a problem called exploding gradients. One way to counterattack that is to clip your gradients. That's a method where basically you normalize your gradients whenever they cross a threshold. The opposite problem of this would be when your values are way smaller than one or less than one. If you have multiple of them, you're going to have a problem called vanishing gradients, where multiplying something multiple times, eventually you're going to end up going very close to zero. Now, there are three ways to alleviate this problem. One is choosing a better activation function. There are different activation function you can use. We'll see some examples. You can use a different weight initialization structure, or you can consider a completely different network architecture that is a bit more complex and doesn't suffer from this exploding or vanishing gradients problem.
George, what do you mean by a different network architecture? Is that just like a whole other way of approaching the problem? Is that?
Yeah. So we'll see that. Remember,
not using an RNN? Would it still be using an RNN?
Yeah, we're using a modified version of RNN, where we are keeping track of all our weights and biases, and also we're controlling the main component, which is the cell state, a little bit better, and protecting it from this vanishing gradients and exploding gradients challenge. So it's a way of updating it a little bit smartly, and being very careful with how does this gradient flow work, even if you have a large network. So we'll see that in a couple of slides.
Thank you.
I'm actually wondering if, well, I'm thinking that vanishing gradients and exploding gradients might be a bigger problem in a smaller network for RNNs, just because you have the same weight matrix that's being used for every step, right? I hadn't really thought about this previously, but if you have, say, large numbers in the weight matrix, then you might get exploding gradients quickly, whereas in a really deep convolutional neural net, the other example where we've seen vanishing and exploding gradients, typically you're going to have different weights at each step along that chain. So that you might have small weights somewhere, but maybe they'd be made up for by larger weights elsewhere.
Mm-hmm.
So I'm wondering if vanishing and exploding gradients become a problem for relatively small architectures in an RNN like this.
Yeah. I don't know if there's a threshold after which, let's say, 3 time steps to run into this issue. Yeah, it really depends on initialization of these weight matrices and the input, how you're encoding your inputs, what kind of embedding you're using, and what is your problem. Is it a really hard problem? Is it just positive or negative analysis? Or are you trying to predict the next word? It really depends on the problem. Cool. Sorry, I was admitting somebody new. So taking a deeper dive in this vanishing gradients and what kind of problems it can cause. Again, we're multiplying, especially in the vanishing gradient problem, we're multiplying many small numbers together. The errors, we have to backpropagate all through the different time steps. And again, we're multiplying with smaller and smaller numbers, which causes the gradients to be smaller and smaller, which causes the weights themselves to be updated by a very small amount. And another byproduct of this is that we are giving bias to the short-term words compared to all the way in the beginning of a sentence. So a visualization here, for example, if you're trying to predict the next word in the sentence, the clouds are in the, and x0 would be the, x1 would be clouds, x2 would be r, x3 would be in, x4 would be the, and we're trying to predict the last word. Probably the and in would have closer relationship to each other. But if you have a sentence like, I grew in France, I had a great childhood, I ate a lot of croissants, I love hot chocolate, blah, 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 and I speak fluent, what? You can have an arbitrary long sentence here, and predicting the next word basically boils down to remembering that the country France and the language French are related. And that length would be arbitrary, and it's very hard for your network to remember this correlation and this relationship. So that's one byproduct of this vanishing gradient problem. Your network won't be able to generalize and remember previous tokens or previous words, and it will not be able to predict the next one sufficiently.
If that ... in the middle is talking about croissants, though, I think you might do better.
Fine, something else. Get my pointer. Awesome. So if you remember, the three ways that we talked about tackling the vanishing gradients problem was activation functions, parameter initialization, and gated cells. And what we're looking at here in trick number one of activation functions is the derivative of different activation functions. So if you remember, ReLU is a linear function, x for positive x, and 0 for negative input. So the derivative would be 0 for a negative input, and it would be 1 for positive input. So that's the derivative of ReLU in dark. Tan h, this is the derivative of tan h. It peaks at 0, and it's less than 1 for all other values. The sigmoid is at the blue one, and you can see that it's significantly less than 1. So as you see, for example, if you use sigmoid in your neural network, you're probably going to get into this vanishing gradient simply because all your outputs are less than 1. So you're guaranteed that at some point you're going to hit the vanishing gradient problem. So to counterattack that, you might as well use the ReLU function, which you know that the derivative is 1 for any positive value or 0 for negative value. So you probably will not run into that problem, or not as fast, I would say. Another technique is to do a proper initialization, and that in deep learning shows up many times. There are different ways to initialize your weight matrices, but a popular way to avoid this vanishing gradient problem is to initialize all your 3 weights into identity metrics and the bias to 0. This seems to have given better results when you're computing the multiple gradients. And another one is using a completely different architecture or a modified architecture of this, and that is based on an idea that is called gated cells, where you are relying on different gates on how to update the hidden state, and also how does the gradients flow using these cells. Any questions before we take a deeper dive to gated cells? Awesome.
So returning to that parameter initialization, what is that telling us? That's the identity matrix is saying that we're initializing parameters to feed the hidden state through the network?
Yeah, so each cell has these 3 weight matrices. And if you initialize them to 0, you're probably going to run into issues sooner. But I think through experimentation, or I'm not sure if this is a proof, but I think through experimentations, if you initialize them to 1, you will not run as quickly to this vanishing gradient problem as you would with some other initialization. Awesome. So this is the network that we have seen so far, and this is the unrolled version of it. But really what we're looking at is a network that takes x at a given time step as input, or takes an input in our case. It takes a previous state as an input as well, runs them through a nonlinearity, a very simple neural network in our case, and produces the new state and the new output. That's basically the basic functionality of a standard recurrent neural network. And this visualization I took from Christopher's blog here. I have a link that explains it really well of the differences between standard and different architectures. So speaking of cells and how do we actually protect the information flow and also the gradient flow, there's a new architecture, relatively from 1997, I would say, called long short-term memory, LSTMs. That are based on different cells. And different cells basically correspond to different neural networks that take something as input, apply a nonlinearity, and produces an output. So one of these cells is called the forget cell, or the forget gate, I should say, because these are called gates in the literature. And this gate takes the current input and the previous hidden state. You'll see many gates do that. They're concatenated, they form a long vector. We have to define a new weight matrix here called WF for forget, and a new bias, BF. So we do our linear operations here. We multiply the weight matrix with a vector, this extended vector. We add the bias. We use a nonlinearity, for example, sigmoid in this case, and we come up with our new output vector, forget. We use the same exact inputs, the previous hidden state and the current input, but in this case, we define a new weight matrix for include or update, as well as a new bias for include or update. We also use the same input of the current input and the previous hidden state. We define two new weight and bias matrices, one more. We pass that through a nonlinearity 10H. That will give us what is called a new candidate cell state. See this tilde here above CT? That's the new candidate cell state. It's not the new cell state. Then we have one more gate. My pointer. Which, well, this is not actually a gate. This is an operation that uses previous results. So we have our previous hidden state, CT-1 in this case. We have the output of the forget gate, FT, which we calculated here. We do a pointwise multiplication. This FT would be between 0 and 1. 0 means that you don't want to include that part of the cell. 1 means let it pass through all the way. And we add it up to the new include or update gate, pointwise multiplication with the new candidate cell state. So all this is saying is forget some components of the previous cell state and include some new components of the new candidate state. That would be your new cell state. So that would be your new CT. And how do we actually calculate the output? Don't get confused by the H. H is the actual output here. Previously it was Y, but H in this block is actually the output. So to actually calculate the intermediate output, I would say we have another weight and bias combination. We use exactly the same inputs as the current input and the previous HT-1. We calculate this output or this intermediate output that is basically a filter of how much should we let the modified version of the cell state, the 10H in this case of cell state, how much should we let it pass through? That would be our new output. So the comparison between a standard RNN on the left and an LSTM on the right is now that we have all these 1, 2, 3, 4 different gates, which control exactly how much of the previous state we should include. We have a new candidate state, C tilde, we have a new output and a new hidden, or a new output HD in this case that we use for the next step.
I just have a notation question. That middle gate is those smaller yellow. Are those sigmoid functions, or are they little C's? They represent C?
Sigmoid. They're actually sigmoids, yeah.
But then we use sigmoid out front of this function here. But I'm talking about the upper right, like in the middle there. Those small, you have tangent H, and then those two in front, and then the tangent. Are those two sigmoids? That's what I'm asking.
So yeah, the sigmas are the sigmoid, tan H nonlinearity, sigmoid.
Okay.
And X means pointwise multiplication.
Yeah.
Plus means pointwise addition.
Okay, thank you.
There's a legend here. So yeah, circle pink means pointwise, and yellow is actually a neural network nonlinearity in this case. And this is we're combining vectors into one, concatenate, or just broadcasting or copying the same vector to two copies. Any other questions regarding this architecture? We're gonna actually use it pretty soon. Cool. Just some other notations. Online, you might see a slightly different notation or slightly different organization. But basically, all you have to do is, I included some other visualizations here from another blog. All you have to remember is that in the standard RNN, we have a recurrence where we use not only the current input, but also the hidden state, and both of them are used as input to produce the new output. And the unrolled version of that is shown here. And the difference between a vanilla or a standard recurrent neural network and an LSTM or modified version of LSTM is that they have this cell state which goes through different time steps and allows information to flow freely. And you'll see how that impacts the gradient, the vanishing gradient problem, and how does that helps us solve that challenge. So when we calculate the loss and the gradients, this new highway, they call it, they use new highway of cell state. As you can see, it doesn't really depend on any weight matrices or any nonlinearity. So you can see that we have actually a pointwise multiplication in addition here. So if you really want to flow your derivatives and your error through the cell, you can do that much easier than what you were doing before. So this is one of the main reasons why LSTMs and modified version of them are pretty good at remembering long-term dependencies, because they have this information highway when you do forward propagation, and the loss and the gradients actually are flowing backwards without much resistance when you do backward propagation. And in TensorFlow, the method and the class that implements this this type of network is called LSTM, where you take the number of units as the input, which is the dimensionality of this cell state. Some more resources. Andrew on his deep learning specialization takes another look at these networks and actually goes in a little bit more detail of how do you calculate the hidden state and the different inputs and the outputs, and also the same or similar equations that we saw before. The difference is the naming convention might be slightly different, and also the visualization might be slightly different. But all you have to remember is that you have your current input, your previous hidden state. Now you have a new concept called cell state, and that actually helps you with flowing information forward in time and the losses and the derivatives backward in time. You can have, you'll see stacked version of them. You can have one layer on top of the other. We'll see that that's more of an advanced architecture. Another one that I wanted to include before we wrap up the theoretical part of this is there are two great papers. One is called LSTM, a Search Space Odyssey, which basically tries to figure out different combinations of those equations that we saw before, and also experiment with different nonlinear functions and also architecture. So basically take those gates that we saw before, try to rearrange them, use different combinations of them, introduce new ones. And basically what that paper found was that none of them really outperformed the LSTM on across the board. Like some version of them were pretty good at specific problem or specific inputs, but there wasn't one that was generally much better than LSTMs. And a similar paper explored again different, I think, evolutions of these LSTM networks, and basically they came to similar results that there wasn't one that was significantly better across the board on different problems than LSTM. Cool. So now the practical side, how do we actually use it, and does it work? Does it give us better results, and does it help us with our original challenge, which was the IMDB review challenge? So if you remember, we had this is our initial challenge that we had. We have our 8,000 subword tokens challenge from IMDB, and our goal is to classify reviews as positive or negative. And we used an embedding layer before. We used a densely connected layer of 6 units here and 1. We used binary cross entropy as our loss function. And if you remember, the accuracy was pretty much random. It was around 50 something %, and we didn't get a lot of good results. And something to remember, we had about 171,000 parameters. Now using LSTM, which is right after the embedding layer here, this is the new component. We're using 64 units, or that's the dimensionality of the cell state. We're using a bigger dense network after that. And looking at, let's look at the parameters first. We went from 171,000 parameters to close to 600,000 parameters, and most of them are the embedding and the bidirectional LSTM. Bidirectionally, in this case, I didn't talk much about it, but basically what that says is that when you're trying to predict the next word for example, in a corpus, you are allowed not only to look at the previous words, but also at the future words. That's what it means. So that you have a network that reads input from left to right. You also have a network that reads information from right to left. That's the only difference. And the number of parameters here, it's basically two parallel networks. One goes from left to right on your input, the other one goes from right to left. The number of parameters will be double that of a single layer.
So, George, in a case like this where we're not predicting the next word or some word that's missing or something, you're not predicting like a part of the sequence. We're predicting, binary positive or negative, right? Is bidirectional really going to do much for us? I didn't try it without it, but I just wondered if it's really necessary.
Yeah, I think I tried different combinations. I think bidirectional helps a little bit. In general case, it helps a little bit. Could be because we have double the parameters. Could be because I'm not sure if I can find a very good example, but maybe when you read a sentence from left to right, sentiment might not be clear, but maybe when you read it from right to left, I'm not sure. We don't read it from right to left as humans, so could maybe the negation was in the end.
You could think of something like, I like this, but it really isn't that good.
Yeah, and you need to give the end part more relevance.
Yeah.
Read
maybe.
from that side, you get. Could be.
Or maybe the sentence is very long and the actual sentiment is the very end. Maybe, I'm not sure.
But the question is, where is the output of the network, right? Because if you think about the way it looks unrolled, you've got this hidden unit, 1, 2, 3, 4, 5, 6, 7 of them, and any one of those could be read as an output, right? Like the named entity recognition task that Andrew shows at the beginning of his course has many-to-many where you have one output for each one. If you're talking about a many-to-one, I think the picture that you showed at the beginning, and it's probably the most common one, has the one output on the far right.
Yeah.
But if you have a bidirectional network and you're training it in that way, does it even matter which? I mean, does it make sense to try to move your output closer to the middle so that you can weight the back end of the sentence and the front end of the sentence roughly the same? I don't know.
Yeah, so the forward network would generate, you'd look at the last time step and you come up with one output. The opposite network would probably generate an output on the very first token.
But if you're using a bidirectional network with one output, is it then combining those two outputs and forming a dense layer from them?
I think so, yeah.
Maybe a softmax just from that?
Yeah, so it would be twice the size of the single layer.
Okay, so that makes sense. So it's like you have two networks, one of them's going all the way forward, the other network's going all the way backward.
Yeah, it's exactly that. And I think Andrew does a very good job. I might include a new visualization here, but yeah.
I think his example of that had a many-to-many where he was trying to predict whether something was a proper name. So he just had a y2 above x2, y3 above x3. In the case where you only have one output, it does make sense, I think, to do it the way you just described, where your forward network, you're reading the output at y4, and your backward network, you're propagating it all the way over to y1 and taking that, and then taking those two vectors and feeding them to the softmax or something?
To the dense layer, yeah. You're flattening and then you're feeding it to the next dense layer.
Huh.
Okay.
Yeah. So no, bidirectional. So using, again, we went from 171,000 parameters to 600,000 parameters. And from pretty random 54% accuracy, now with just 10 epochs, we're about 85% accuracy. And the good thing is that we're not overfitting anymore. One issue we had before is that training and validation accuracy and loss were pretty much diverging. So we were definitely overfitting. Here, the two graphs are much closer to each other and they follow a general trend. So we are doing much better in terms of generalizing to the test set, but also not remembering the training corpus and not being able to predict the sentiment on the test or validation corpus. We had one layer of LSTMs. In deep neural networks, you can have as many layers as you want. In this case, we added another bidirectional layer as an output of the first bidirectional LSTM layer. And if you want to do that, you have to make sure that the first LSTM layer actually returns sequences instead of just one value. By default, I think this will return just one value. So if you want to actually return the entire many-to-many outputs, you have to return a sequence as true. So now, I should introduce a new visualization here as well. Now, if you have, let's say, 10 inputs or 10 tokens, and you're outputting 10 tokens, those 10 tokens are actually used as input in the next layer, which are with a lower cell dimensionality here, 32. Then that one is only producing one output. Again, it's bidirectional, so it's a concatenation of two tokens, as we talked about, or the two outputs. That is fed to a DNN that is giving you only a 0-1 classification. So now we introduce the new layer, bidirectional layer. We have another 40,000 parameters here, and we went to 635,000 parameters. And performance seems a little bit better, a little bit more stable, but it's not, orders of magnitude better, I would say. Maybe the training set, if you want to compare, no, even that approaches 95% pretty towards the end, towards the 10th epoch. So that one actually crosses it. So the capacity of our network basically increased, so we're able to increase our performance on the training set, maybe a little bit on the validation set as well.
No, it's worse.
Yeah. Yeah. 85. Yeah, then it dips a little bit, yeah. I want to introduce this visualization here, this chart from this Stanford lecture on recurrent neural networks, where you know, how many layers deep can you go in RNNs and LSTMs? You know, is it always deeper the better? And there was just on a very basic, I think, search here on a very basic corpus. They saw that. So the dark one is, I think, using a corpus of 20,000 words, and this one uses a corpus of 10 times more, 200,000 words. But you see that you get better performance around 3 layers, and after that, your performance deteriorates. So more layers stacked above each other in terms of LSTM is not always the best approach.
There's always something that they tend to reduce the units, so they tend to half them in each layer. You tend to, there's some kind of standard around that I've seen too.
Like empirical.
Yeah, it's typically what they've shown here is typically what I've seen. I've never run a test.
Yeah, I'm not sure if this is related. Remember, Robert, when you were talking about convolution networks, that the image gets smaller, but the depth gets larger.
Right.
I don't see that here. I see, you know, input to output end to end. So I'm not sure. You know, I don't have a good explanation of why it would have it. I mean, I don't know. That's a general.
You know, in that Stanford study, I assume they were keeping the layer number of units in each LSTM layer the same. Is that right?
That's a good one. Yeah, I'm not sure. Yeah, that's.
I'll watch the video.
Yeah. Okay. Another approach is we could use something called 1D convolution, where we've seen the 2-dimensional convolution, but the 1D convolution is basically looking at a time series at an order set, and you're applying some kind of a weight combination to a window subset of that input. So if we do that with this data set here, if we're looking at the embedding layer again, we're introducing this convolutional 1D layer using this railer activation function. To actually lower the dimensionality of it, we introduced this global average pooling 1D, which in this case, I think we have 128 by 5 units. It will average across all 5 dimensions of this conv 1D. And then it's followed up by a dense network. So this architecture has about 500, 600,000 parameters. It starts pretty well, above 85% accuracy, but you see a huge gap between training and validation set. And we are pretty much overfitting here, especially as the validation accuracy on the test, on the training set approaches 1.
I think to go back to that global average pooling thing, I think there's a sequence length. There's a max length that's not shown there for some reason, but you're actually averaging over the whole sentence, not over the 5 layers in the convolution.
Oh yeah, you're right. Yeah, the challenge is that you could have different inputs of different lengths. Yeah, you're absolutely right. So you could have a 3-token sentence or a 100-token sentence.
Right. Yeah.
How do you make sure that your network can read that regardless of the size? So that's where you're taking the average, I guess.
Yeah, I think the one that Lawrence showed in the video had a fixed length with padding in that embedding layer. So maybe you can, I guess because you're doing a global average pooling, you don't actually have to have a fixed length.
Plus, this screenshot, maybe I cut it. I'm not sure if it had more after this. I'll have to take a look.
Well, I think it's it looks like the parenthesis closes the embedding part, so it's just the comma to take you to the next line.
Yeah.
But I think that input length parameter on embedding is optional. and you can choose to use it if you want to do things like flatten or feed to dense layers, where you have to specify a certain size. But if you feed it to something like a global average pooling, then you don't have to specify the input length at all, because it's just averaging. And so it's just it can average over a 5-word sentence, or it can average over a 100-word sentence. It's all the same. It's still feeding one shape to that next dense.
Yeah, I can experiment probably with omitting that and seeing how does it behave. Good observation. So here we're introducing another convolutional 1D layer right after the first one, followed by a global average pooling as well. The number of parameters increased a little bit, but the accuracy and loss are pretty much the same, I would say. Again, we have the same overfitting problem here. And if we compare it to the previous one, maybe a little bit higher. Yeah, the accuracy on the validation side is a little bit higher. What is interesting is that the trend is downwards on the validation side as the weight gets updated. Then we introduce a dropout layer here, only one convolutional 1D layer and a dropout. That seems to be a little bit more stable and fix a little bit the overfitting, but still it's not enough. You can tell that both visualizations and charts are diverging, both time series. Cool. Any questions before we look at a completely different data set? This is the IMDB subword data set, and we're trying to classify sentiment.
I just observed this, that even with the LSTM, but with all these, it's like your network basically learns everything it can in the first epoch, and then really there's nothing being learned that's of use to predict better than what you're already predicting. You know what I'm saying? It's like, yeah, we never really figure that out.
The trend, right? The trend that the validation accuracy is actually downtrending, you're saying?
Yeah, it's staying the same or downtrending. The best results are usually the first epoch, or the second maybe, but it's usually.
Do we know why that is? Is it just that we're using small data sets where you can't expect more training to improve much after one?
I think it's because we're learning these embeddings on our own. That also has to do. So the quality of the embedding is also very important.
But we're not learning much, is my point. We're learning.
Yeah.
You know?
But we're creating our own embeddings, right? We are representing this 64 dimensional space, the words on our own.
Right.
But it is curious that compared to the examples we saw when we first started with neural networks, and you showed gradient descent improving at each step, and here it seems like the first step and then you're done.
Yeah, it's almost like a transfer learning exercise where there's not much else you can fine tune. It's got everything it needs. And
yeah, but from a training perspective, from a training data set perspective, you're doing a better job. But yeah, you're not generalizing enough to capture the validation data set.
From a prediction point, it's not really getting any better.
Isn't a lot of learning like that, where you know absolutely nothing, and then after the first semester, for instance, of a course, or you're studying a language? I mean, if I study Arabic, I don't know anything about it. Then getting beyond to get to fluency, to get really good, that's where it gets really hard to learn more each. I mean, there's just a big jump when you don't know anything to knowing a good bit about it.
Yeah, that makes sense. In this case, we're kind of forgetting though as we're going more deeper and deeper, or we're actually memorizing the textbook, or we'll talk to somebody. We're not doing as good of a job as we did last month, for example.
Yeah, we have that same example of validation loss increasing while accuracy is staying roughly flat. I think it's the same thing that happened previously, where our training set is doing so well that the way to reduce loss on it is just to become more and more confident on it. And then that ends up costing you when you're not doing as well on the val set.
Yeah. Cool. So one more data set and one more approach that we'll explore. So the new data set is actually much larger. It doesn't contain 8,000 words. It contains millions of words, and those words come from 1.6 million tweets. And this data set is again a sentiment or classification challenge where we are classifying a tweet or a corpus, a sentence, into negative sentiment or positive sentiment. The original data set actually has a neutral sentiment as well, but I think this model that we're using, or this data set we're using, we're completely ignoring the neutral ones. We're only considering negative and positive. So this is a labeled data set. It has the label, the target, an ID, a date, some internal flag, the user, and the actual text. So if we look at some examples, the label is 0. 0 is negative. I was out most of the day, so I didn't get much done. I have no time, 0. So if you look at all these 1.6 million tweets, you're going to see some positive ones, and it's a labeled data set basically. But yeah, this is the new data set. And the other component that is new is instead of learning our own embeddings, we're going to transfer learn embeddings from a completely different architecture or paradigm called GloVe, and that stands for Global Vectors for Word Representations. And I will link here to the paper, but basically this is looking at an unsupervised learning algorithm where the goal is to obtain high quality vector representations for words, right? So they did that looking at word-to-word co-occurrence. So they look at great day, like different combinations of words. They saw which words co-occur together. That means that their representation will also be closer to each other. And I mean, higher. The training set was massive for this. It was 5 different actually data sets. It was a 2010 Wikipedia with 1 billion tokens, 2014 Wikipedia with 1.6 billion tokens, and some other data sets from the internet, the Common Crawl, that had basically a huge training set. And what they showed is that when looking at, so diagram A here in the example, when looking at word analogy. So they have different tasks. One of them is word analogy. So X is to Y as something else is to what, and that's a word analogy. So they showed that this word representation performed much better than the previous approach, which was the back of words. And also in some other tasks, it performed much better. And this approach actually introduced the relationship between words that we briefly mentioned last time. So this is where you can explore those relationship between, as we saw, a man man plus king.
King minus man.
King minus man plus woman equals queen. You can do all this vector space transformation, and you can move. You can also do company CEO, city, zip code, strong, stronger, comparative, superlative, and all that. I've also seen city, country, city, capital, sorry, so country, capital. You can do all kinds of interesting associations. So using this new data set and this new word representation, let's see how our network looks. So now the embedding, this is the new data set. We're learning it from scratch. We have some embedding dimensionality here. I think it's 16. and an input length, I think, of 100 tokens, and it's followed by a DNN. And so you can see here we're overfitting a lot, and you can also see the similar result that we're doing pretty well in the validation set in the beginning, but then after a while we're just going lower and lower in accuracy. And same with the loss, we're diverging from early on until later on, we see a huge difference. But in terms of accuracy, we're about 70 something percent, between 75 and 80 on the validation, and we're dropping below 75%. So if we introduce this learned embeddings, and the way we do that is you can actually download them, and you can look at each one of them, and you can associate to each word in the corpus this coefficient or these embeddings. And then once you have this matrix of word to vector combination, you look at your own tokens. Our own tokens are contained, remember, in this word index dictionary. If for a word in our tweet data set we have an embedding from GloVe, we associate it. Otherwise, we use our own. But hopefully this large embedding from GloVe, since it's trained in billions and billions of words, hopefully it will contain most of our words, and we'll be able to use the learned embeddings. In terms of
do we use our own, or I think it sets it to 0, right? Isn't that what's going on when we're initializing the embedding matrix up there?
Oh, yeah.
I believe we don't do any. I mean, we do. I guess it learns it as it goes, so we sort of are using our own, but we initialize it at 0. That's my understanding, right? And
yeah, in this code, maybe it's somewhere else. In this code, I don't remember the initializing to 0. But yeah, I think you learn it on your own. I think in a new word,
because he's also setting trainable equals false down there on the embedding layer. So I don't know. I hadn't looked at that, but I thought maybe we don't.
Good one. I'll check and have a closer look at that just to make sure.
Yeah, it also says if you look at the previous slide, the number of trainable parameters is really small. Previous slide, or is it the next slide? This one.
Yeah, exactly. Yeah. So we're not learning the embeddings. Yeah, we're freezing the embeddings. We're freezing all the first layer weights. We're not learning anything there. Yeah, trainable false right here, and weights are the actual embedding matrix, which is word to vector coefficients. And again, global pooling and dense tense. I just wanted to point out the length, or how many different tokens this embedding matrix had, and it had about 138,000 rows. And the English dictionary has actually 171,000 words. So we're getting pretty close to the entire vocabulary there. Okay, how does it do? So first of all, just considering the architecture above, there's a reminder of this one here. Good news, we're not overfitting. Validation and training and validation accuracy are pretty hand-to-hand, go together here. Same with the loss, so good news is we're not overfitting. Let's look at accuracy. We're about 71%, 71% on both training and test. Whereas previously we were at 75 for validation and almost remembered everything, 95 plus for training. So we dropped in accuracy, but at least we don't have the overfitting problem anymore with just this combination of global average pooling. If we remove that global average pooling and we introduce the, if you remove it, or if you after that, I'm not sure. I think after that, if you introduce a bidirectional STM with only one bidirectional STM layer with 64 units, the accuracy jumps from 70s to 76, 78 here, but we run into this divergence problem of overfitting a little bit. If we add another layer after the 64, we have 2 layers of bidirectional 64 units, and followed by the dropout. The validation accuracy is a little bit more stable. That's probably due to the dropout, or as well as the new layer. But still, we have this overfitting challenge. And our accuracy might have improved a little bit. It's hard to tell, but again, this is trained just for 10 epochs. If we use the 1D convolutional followed by a global average pooling, the overfitting seems to be not as big of a problem as before, but the accuracy is around 75%. If we do 2 of those, followed by a dropout, 75 again, not that much of a difference. If we do initially a dropout right after the embedding, then a conv 1D, then a max pooling. This was average pooling, now we're doing a max pooling here. And then an LSTM, things are not overfitted anymore, and we're about 76%, 75, 76, so much better behavior. The last one that I tried was a dropout, conv, max pooling, and 2 of the LSTMs, and a little bit better, except for this drop here on epoch 1.
So it's interesting, right? All these are trying to reduce overfitting in a way so that we improve our ability to generalize and predict unseen data, which is our validation, right? But we still only get like 77% for everything, you know, and we never get better than we did at the start. So I found that very interesting. I'm not sure I can explain it.
Yeah. Also, do you think if training for longer would have helped? I think you might have helped a little bit, especially for the ones that are not overfitting, like
yeah, maybe that last one. Yeah,
this one, or just a very basic one, the first one.
Right. It's hard to say. I mean, I don't...
Yeah, this is where exploring different architecture designs, right, is very important, because at least we don't have in many architecture or several architecture don't have the overfitting challenge that we had in the beginning where we learned our own embeddings.
Right.
In all of these cases, the optimizer is Atom, is that right?
I think so. I have to check.
I think
I have it included here.
You're using all the code from, well, yeah, from
Yeah. Yeah, loss function is binary recursive entropy. I think the loss function is.
Well, my question would be, was the effective learning rate possibly on these things? And so, like when I think,
yeah, you're getting into hyperparameter tuning. Yep, different activations, yeah, different learning rates.
And that's always the one I always think of looking at first. And when I see especially like the choppy, the choppy loss, that's kind of, isn't that an indication that it might like be bouncing around, like the learning rate might be too big, it's bouncing around in a global minimum, that kind of thing.
Sometimes that can also be a feature of batch size. I've seen that also. Batch size will impact that. I believe at one point Lawrence during this course mentions that also.
Batch size.
Yeah, it's another thing. It can boost some of that choppiness.
Is how would you, if you write, if you don't know, that's fine. But if I wanted to play with the learning rate in Atom, how do you write the code for that?
Oh, we're going to do that pretty soon. Yeah.
He goes through that pretty extensively.
Yeah. There's a whole chapter, but basically the way you do it, go ahead.
Is it in week 4 or?
That's actually in course 4, but I'll give you the quick version of it. What you do is you have your architecture. TensorFlow has a method called rate scheduler, where basically you say, okay, try different weights, different learning rates, and you can actually plot the loss versus learning rate, and you're trying to find the learning rate that minimizes your loss. So once you do that, then you go plug in that learning rate to the same network or maybe a larger one, and hopefully that will give you better results.
Okay, so it's not a matter of just like giving passing a parameter to, or specifying a, you know, an attribute of Adam and saying learn it LR equals something or something like
Yeah,
that.
so all these optimizers that change the learning rate on their own, right, based on first momentum or second momentum, they're going to modify the learning rate no matter what. But
Is that what Adam does? It's an auto adjusting kind of thing?
yeah. It's not constant. Yeah, absolutely. Yeah, but where you start is important, because if your learning rate is pretty large or pretty small, where you start is very important.
Right.
And then gradually over time, how much it dampens and how much it gets smaller and smaller is also very important.
Mm-hmm. Okay.
I want to show you just for 1 minute, because I have found a very good visualization of that. So in this AI notes, there's a good explanation and a good visualization of different optimizers. Yeah. So, I mean, this is a little bit artificial, but let's say your loss function looks a little bit like this, where it's 3-dimensional. So the 2 x-axis are the weight. Let's say you have a problem where you're modifying your weights, and there are only 2, W1 and W2 in this case, and the y-axis is the loss. And then what you're doing here is you're comparing different optimizers like gradient descent, momentum, RMS prop, Atom, where gradient descent probably going to keep the same learning rate, and the other ones are going to change the learning rate based on first and second order momentum. So you start from this point, and you'll see the purple one is here. Purple one is momentum, orange one is RMS prop, yellow one is Atom. So momentum was the first one that significantly went much faster. If you look at a different landscape where the minimum optimum, so you can see the minimum is right here, and you can also change where you can start as well. So let's say we start from here. Play. So again, the momentum looks like it's converging this local minimum. If you see here, they're all stuck at this local minimum, and the loss or the cost function is just not getting lower than that. Let me move so that's the initialization. That's very important, right? Let me move it to right here. It looks like it went to this other local minimum. So maybe if you start in the middle, better chances. No. I guess it really is really sensitive to where you start. So okay, this is kind of artificial, but I assume we'll go to the actual true one. Okay, there you go. So the momentum is going first, but it's a little bit bouncy, and the other ones are catching up as well. Yeah, you can try, and this is more, well, better behaved, so probably this one will behave a little bit better. But I think this one is one there's no, or the minimum is, I think outside your region, so you always keep iterating. And this one, the local minimum is there. Well, this is diverging like crazy. So this is now, the learning rate is probably too high. So that's, I don't know if you can make it less than 0.001. Or maybe introduce rate decay and interesting other approaches. But you can see it's diverging here. Okay.
So if rate decay is 0, does that mean that the learning rate won't change during?
Yeah, for the gradient descent, yeah.
Okay.
The other ones will.
What about they all had a setting for that?
Yeah, the other ones will change it based on first and second order momentum, but I think you can introduce your own decay even after that.
Okay.
Cool. That's all I had for this week. I took down some notes on exploring some more topics based on your feedback, so that was useful. Any feedback, comments, questions?
Just one question. Do you have? I saw last week we had the notes for like just some different things we discussed. It looked like that last was deep learning AI notes, I think it was, but I didn't. 2 weeks ago I took notes. This time I didn't. Is there going to be just a spot for that? Some of these resources?
Yeah, I can post them on.
That's all I was asking.
Made up. Yeah, absolutely. Yeah.
He's also recording.
Oh, true. Yeah.
You can watch it on YouTube.
Yeah. Any other questions?
That was great. Thank you so much. It's
Cool.
fascinating.
Very excellent.
Yeah.
Really interesting.
Try to combine multiple sources and try to also, myself try to understand it from different perspectives and fine-tuning your network so that you get better results. Awesome, Dan. This was a fun adventure. We're course 3, week 3. Next week, we're going to cover the last week for course 3, and we'll actually look at training a recurrent neural network on a large corpus. We're actually going to train it on the entire all sonnets from Shakespeare. We're going to give it an input, a sentence, and we'll allow our network to generate the next word and the next word and the next word, and we'll basically be able to generate a whole sentence for us. And the cool thing is the input sentence could be anything, but as you'll see, the output sentence is highly correlated with your training corpus. And after that, we have our deep learning happy hour as well. Week 4 is a little bit short, doesn't have a lot of content, so I recommend we go over the trivia as well. Yeah, I posted it in our meetup. Check it out. It's open. You can practice. Should be a fun adventure.
Thank you, George. Really good.
Cool.
Yeah, thank you.
Thank you, everyone. Thank you. Appreciate it.
Good night.
Yeah, that was great. Thank you.
Awesome.
Mm-hmm.
Have a good night, everyone.
Okay,
Thank
good
you.
night.
Night.
Good night, everyone.
Thanks, George.